What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 3, Section 7, Inverse Functions. Let's do it. Described by the horizontal line test is an effective way to determine whether a function is one-to-one. So, in order for a function to be a function, first and foremost, it means that it must pass the vertical line test. And the vertical line test essentially ensures that there's no input that is repeated. So, for example, this would fail the vertical line test. This would not be a function. Okay, so we know that if it's a function, it's going to pass the vertical line test. So let's look at a hyperbola, for example. So now we ask the question, is this, how do we determine whether this is a one-to-one and maybe applying the horizontal line test? Now, what is one-to-one? It means that there's only a unique input-output relationship. So for example, this is not that case because look, let's say for example, this point is going to be -2, 4. We'd also have a point over here that might be +2, +4, but now that output value is repeated. So the vertical line test, by calling it a function, we already know it passes the vertical line test. We're not going to have any inputs repeated. But again, we need that one-to-one relationship with inputs and outputs. Everything must be unique, but here the horizontal line test would show us that since we have 2 or more hits with the horizontal line test, we're going to have an output repeating, which means it is not one-to-one. So this is why the horizontal line test is great to disprove that something is a one-to-one function. Boom, done. Can a function be its own inverse? Explain. This would be true, and I'm going to show you with 2 examples. So if we take first this example of y equals 1 over x, how do we get the inverse? The way we get it is we switch the x and y values, right? So then I make it x equals 1 over y, and then you can isolate the y. Well, in this case, if we isolate the y, multiply by y, we get xy equals 1, divide by x. Well, check it out. The inverse is the function itself. Another example would be y equals x, right? To get the inverse function, we just flip those variables, x equals y. We kind of replace the x with y and vice versa. Well, it's still the same function. So those are 2 examples. Boom, done. To find the inverse of a function algebraically, you're going to start with that function. You're going to replace the f of x with y. Then you're going to swap the variables and then isolate the new y. So I'm going to show you an example. So let's say we start with f of x equals 3x plus 7, and we want to find the inverse. So first I'm going to replace with y, and then we got that. Now I'm going to swap the x and the y. And now we're going to isolate y. So I'm going to subtract 7, and then I'm going to divide by 3 to isolate that y. So now I have y equals x minus 7 over 3. And then to write this in the correct format, that y is the inverse of function f. So it is f of -1, that is implies inverse, of x equals x minus 7 over 3. Boom, done. So for this one, to find the inverse, first I'm going to write it as y equals x plus 3. Then I'm going to swap the x and y. So we got x equals y plus 3. Now I'm going to isolate the y. So I'm going to subtract 3 from both sides. And I'm writing it as y equals x minus 3. Of course, I switched the sides of x and y, which no problem, right? It was going to be x minus 3 equals y. We swapped it, no big deal. And then this is the inverse. So to write it correctly, it's f of -1 of x equals x minus 3. Boom, done. To find the inverse, we're going to start with y equals 2 minus x, and then we're going to swap the x and y. So x equals 2 minus y. I'm going to subtract 2 from both sides. Boom, I get -y equals x minus 2. Then I'm going to divide both sides by -1. Y equals -x plus 2. Okay, and then I'm going to switch it around when I put it back into the function notation. So again, this y is the inverse. So f -1 of x equals -x plus 2. Boom, done. First step to get the inverse, I'm going to call this y equals x over x plus 2. Then we're going to swap the x's and the y's. So now I have x equals y over y plus 2. And then we got to isolate. My first step is I'm going to multiply both sides by the denominator. I want to destroy that fraction. So I got x times y plus 2 on the left side. On the right side, when I multiply by y plus 2, these are going to cancel out. And now I just have equals y. Then I'm going to distribute this guy. So I got xy plus 2x equals y. My next objective, since we're trying to isolate y, is to get that xy to the right side. So I'm going to subtract by xy on both sides. Check it out. Now I have 2x equals y minus xy. Since I want to isolate the y, I'm going to factor that y out. So this is the next step. factoring the y out, and I got 1 left here minus x by itself here. Last but not least, we're going to divide both sides by 1 minus x. So I've got y equals 2x over 1 minus x. And now I'm going to put it back into function notation. I'm going to put the y, or the inverse of f, on the left side. So f negative 1 of x equals 2x over 1 minus x. Boom, done. And just as a quick caveat, in the answers, they have it as negative 2x over x minus 1. Just want to point this out. This is the exact same thing. These are identical. All they've done is they factored out a negative 1 in the denominator and thrown it up top. I like this way better. I'd rather not have a negative numerator, but they're exactly the same. So for this one, we want to find an interval where it is not decreasing, aka increasing, and we want to make sure it's 1 to 1. And the reason why we need to restrict the domain is because this is a parabola, right? It's a parabola centered at negative 7 comma 0. That's going to be the vertex. So here's negative 7, 0. And you see this fails the horizontal line test, so it's not 1 to 1. So to make it compliant with the horizontal line test, we need to remove this section. So my domain is going to be limited from negative 7 to infinity. Now that we have this appropriate domain, let's go ahead and find the inverse. So again, I'm going to switch out the f of x with y like so. Next, I'm going to swap the x and the y. So x equals y plus 7 squared. And then I'm going to isolate y. So first, I'm going to start by taking the square root of both sides. So we got square root of x equals y plus 7, right? The square root destroys that square. Then I'm going to subtract 7 from both sides. Square root of x minus 7 equals y. And again, this is my inverse, so now I can put it in nice function notation. I'm just going to swap the sides just to make it look nicer. So now we have f negative 1 of x equals radical x minus 7 with that domain restriction applied. So there is the inverse, there is the domain, boom, done. Once again, we have to restrict the domain because this is a parabola and it's going to fail the horizontal line test. This parabola happens to have a vertex at 0 comma negative 5, right? That is based on vertex form. So we know the vertex is there. And so if we just remove this left-hand side with the domain restriction, we're going to have a 1-to-1 function. So check this out. My domain is going to start at 0 and then go to infinity. Now that we have the domain restriction, let's go ahead and find the inverse. So my first step was to replace f of x with y. Now we're going to swap the x and the y like so. And then we're going to solve for y. So first I'm going to add 5 to both sides. Boom. And I get x plus 5 equals y squared. Then I'm going to take the square root of both sides like so. And I get y equals the square root of x plus 5. Last but not least, let's put it in function notation. And I'm going to put the y on the left-hand side, turn it back into f of negative 1 of x equals square root of x plus 5. So here's your final answer for the function inverse, and here is the domain. Boom, done. For these two, it says use function composition to verify that these are inverse functions. So how do we do that? Well, in order for these to be verifiably inverses of each other, it needs to be such that f of g of x needs to equal x and g of f of x, meaning plugging in f of x into g of x, needs to also equal x. So let's see if that's true. So for f of g of x, what I'm doing is I'm taking g of x and I'm plugging it into the x for f of x. So I'm going to rewrite it as the cube root of g of x on the inside, replacing that x. So we got x cubed plus 1, and then that minus 1 is still there. So check this out. These two cancel out, and I'm left with the cube root of x cubed. Well, guess what? That is x. So this one has been verified. Now we need to do it the other way. So again, now I'm taking f of x, I'm taking this whole function, and I'm plugging it in for x. It's x to the cube power, something to the cube power, and I'm replacing that with the cube root of x minus 1, and then we still have that plus 1 on the outside. Now, cubing the cube root of something is going to just cancel out that cubic root. So now we're left with x minus 1 plus 1. These are going to cancel out. And once again, we're left with x. That means the second condition is verified. They are indeed inverse functions. Boom, done. So for this one, we're going to use Desmos for our graphing utility, and we're going to check to see if these are 1-to-1. So as you can see, for y equals square root of x, at every point I could draw a horizontal line, and I don't think I'm going to hit the function twice at any point. As such, since it passes the horizontal line test, obviously passes the vertical line test because it is a function, passes the horizontal line test, which means this is indeed one-to-one, boom, done. For this one, we're going to use a graphing utility to check if it's one-to-one, so let's do that in Desmos. So this is creating a line. It is, of course, a linear equation, and you can see at every point, right? It's just a straight line. It's going to pass the horizontal line test everywhere we go, which means that this function is indeed one-to-one, so we'll say yes, boom, done. For this one, we're looking at the graph, and we can see based on the horizontal line test, check it out, boom, I'm hitting the function more than once. I'm hitting it twice. Therefore, this is not a one-to-one function. Boom, done. For number 25, the question is f of 0 based on the graph. So what does f of 0 mean? It means what is the function value when x equals 0? So that looks to be right at this point, which means that f of 0 is a function value, aka a y value of 3. Boom, done. So here we're trying to find f inverse of 0. And if we think about a function, right? If we have a function and we know that x comma y exists on that function, for the inverse, it's going to be y comma x. That same point, but with the x and y flipped, must exist on the inverse function. So when we think about this, when you say, hey, what is the inverse, the f inverse of 0? What that's saying is, it's like looking at the original function graph, which we have. We don't have the inverse function graph. It's like looking at the regular graph, and really, it's like plugging 0 in for y, right? So we look at the coordinate where y is equal to 0, and that occurs right here. So f inverse of 0 is now going to be the x value of the original function, because the x value of the original function is like the y value on the inverse. So this becomes 2, boom, done. So here we're trying to graph the inverse function of f, right? So there's a couple ways to look at this. The first thing we want to recognize is that the inverse of a function will always be symmetric across the line y equals x, which is what I've drawn in here. So we know it's going to be a symmetric across this way. So we could say like it's going to look roughly like this. Now to get a little bit more accurate, I'm going to choose a couple points. So I see this point as 2, 0. So the x's and the y's are going to be flipped on the inverse, which means that 0, 2 is going to exist for the inverse function, which is right here. So we already have 1 point. Then I see another nice point right here, which is 6, 2. That means 2, 6 is going to exist on the inverse, 2 and 6. So now we got 2 points. Now we're going to look at this point, which is 4, 1.5 approximately, which means we should have 1.54. So that's just rough. So now we got 3 nice points, and I'm going to connect the dots as best as I can. And there is a nice approximation of f negative 1, boom, done. So this question asks if the complete graph of f is shown, find the domain of f. Well, here's the thing. So if we assume that this arrow doesn't exist, and this is a point, and I think this is an assumption we're making here, if they're saying the complete graph is shown, then we see the domain is only going from 2 up to 10 inclusive. And this is the answer given in the back of the book, but I do want to caution you that with that arrow in general, we generally infer from that this is continuing on forever. So if we were to pay attention to the arrow, I would say it'd be 2 to infinity. But if we're making this assumption that this is a complete graph and that's a point, not an arrow, we would go with 2 to 10, boom, done. So here we are assuming that it's a one-to-one function and finding the inverse. Now this goes back to that idea that if I have a function value and I know that it's x comma y that exists on the function, for the inverse, y comma x is going to exist. So that's exactly what they're showing you here, right? We know that the point, when it says f of 6 is 7, we know that the point 6 comma 7 exists, which means that we know for the inverse 7 comma 6 exists. And this is what they're saying here. What is f inverse of 7? So f inverse of 7 is 6. That's the output value, boom, done. Now for this one, we know that for the inverse, the point -4 comma -8 exists. And that's what it's saying, right? When the x value of the inverse is -4, the function value is -8. Now they want you to find f of -8. Well, here's the thing. One thing we know that when we have an inverse function and those coordinates, the same point is going to exist on the regular function, just flipped around. So that means that the point -8 comma -4 exists. And this goes back to this idea. Then what is f of -8? Meaning when the x value is -8 for the function, what is the corresponding function value or y value? It's right here. it's -4, boom, done. So here we're trying to find f of 1, and what does that mean? It means what is the function value, the f of x value, when x equals 1. That's what this means. So when x equals 1, the function value, the corresponding function value is 0. That's the answer, done. For this one, we want f inverse of 0, meaning, when the inverse function has a x value of 0, what is the corresponding y value? Well, this is the same as asking for the original function. If the y value is 0, what is the corresponding x value? So we can go to this function. We can say, oh, here's f of x when f of x is 0. And the corresponding x value is 1, which means for the inverse of 0 would be 1. So the answer is 1, boom, done. Use the tabular representation in table 7 to create a table for f inverse of x. So check this out. The cool thing about a function and its inverse is to get the corresponding inverse function values, you just swap the x and the function value. So you see here, we've got 3 and 1. So to swap those, it would be 1, x, and 3 for the inverse function value. And you can go through this for all of these pairs. So this would be 4, 6. This would be 7, 9, 12, 13. And last but not least, 16, 14. Boom, done. So for this one, we're going to find the inverse, and then we're going to graph the function and the inverse using Desmos. So once again, we're going to say y equals x cubed minus 1, and then we're going to swap the x and the y like so. Then we're going to isolate the y. So we're going to add 1 to both sides. Boom. We get x plus 1 equals y cubed. Last but not least, take the cube root of both sides, and we get y equals the cube root of x plus 1. And then to put it in our function notation, it's f inverse of x equals the cube root of x plus 1. And just by the way, in the book, they have it as x plus 1 to the 1/3 power. These are identical. To the 1/3 power means taking the cube root of x plus 1. Okay, now let's graph them. So here we have the original function in red, the inverse in blue, and look at this nice symmetrical pattern it makes. That's what we should see when we have two functions that are inverses of each other. And you'll notice that it's symmetric about the line y equals x. And again, that's exactly what we should see. We should see y equals x kind of cutting right down the middle. So these are the answers. Boom, done. For this question, we're meant to take this function, which converts Celsius to Fahrenheit, and find the inverse. So let's do that now. Once again, we're going to say y equals 9/5 x plus 32. Then we're going to swap the x and the y. So we got 9/5 y plus 32, and then we're going to isolate the y. So first, we're going to subtract 32 from both sides, like so. Then we're going to multiply both sides by 5/9. So we got 5/9 times x minus 32. 5/9 times 9/5 is going to cancel that out. So we've now effectively isolated y. Now to put it into correct function notation, we've got f inverse of x equals 5/9 times x minus 32. And just as a quick side note, even though this is our final answer, this is what you would use to convert Fahrenheit to Celsius. So see, the original is converting Celsius to Fahrenheit. This converts Fahrenheit to Celsius. Boom, done. Last but not least, we're asked to find the inverse of d of t equals 50t, but they want the inverse to be t in terms of d. So this is a little bit different because instead of going through the typical protocol of replacing it with d and then isolating the d value and so on and so forth, I'm going to leave it as is because really what they're saying is they just want time as a function of distance, aka isolate the t variable. So what I'm going to do is I'm going to say d equals 50t, and I'm not going to swap them. Instead, I'm going to divide both sides by 50. And now we have t as a function of d equaling d over 50. This actually now allows us, if I know a particular distance traveled, to find the time that it took to travel that distance. So they want to find t of 180. So what is this asking? They're saying, what is the time it takes to travel 180 miles? So we're going to plug and chug 180 over 50. This reduces or simplifies to 3.6. So what is that? That is 3.6 hours to go 180 miles. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.